Now, under equilibrium, we are going to talk about a reversible reaction. I'm going to talk about a reversible reaction. I'm going to talk about the equilibrium law and equilibrium constants. We're also going to talk about reaction coefficients. We're also going to talk about dynamic equilibrium. Under the dynamic equilibrium, we're going to talk about heterogeneous and homogeneous equilibrium systems. I'm going to talk about them. Then from there, we are going to solve a lot of questions. The questions, I'll just try my best to. And we are also going to talk about Le Chatelier's principle. That's if we have time. If you don't even have time today, we can finish that one up next week, God willing. There's no anything difficult. We're just reading. Then we are done. From there, we see the next 2 weeks that we will be left to go to school. We will see if we can do redox reaction or solubility, any of them, any of the two. The MNC, we will try and finish up before you go. When you come and you still want us to continue, we will do our best to listen, teach you the rest. Thank you. So today we are doing chemical equilibrium. Now, when we talk of equilibrium, you know, equilibrium is in is in physics, and it's also in chemistry. Now, when we talk of equilibrium, we are talking about a point where something is, what do you call it? I don't want to use come to rest, but something is at peace. Let me put it that way. So, for instance, if you have if you have water and you decide to put your hands in the water or you shake the water in the bucket, you realize that the water will be shaking. Now it will get to a certain point whereby the water will calm down or will be at peace. When that happens, you are seeing that the water is at equilibrium. Now when you play a football, it will roll, it will keep rolling. Now when it gets to a point whereby it is becomes stable, then you are seeing that it is at equilibrium, or it is at a stable equilibrium. When you do physics, you talk about the different types of equilibrium: the neutral equilibrium, the stable equilibrium, and the unstable equilibrium. You talk about that. Now, in the chemical equilibrium, we are talking about certain reactions being at equilibrium. So basically, that is it. Now, under equilibrium, we are going to talk about something called reversible reaction. When we talk about reversible reaction, and then basically we are trying to mean that I'm coming, please. Someone might call inside this one, so let me just. When we talk about reversible reaction, then you realize that anytime you write reactions in a normal experiment, anytime you write reactions, you write maybe A plus maybe B, A plus B maps to C plus D. This one is a typical example of an irreversible reaction. This means that the reaction cannot be reversed. Now in the equilibrium, we are going to talk about reversible reaction. Now when we say reversible reaction, the reactions can be reversed. Now here we are going to consider the forward reaction and backwards reaction. And so that means the reactants are moving towards the product side, or they are forming to form the product. And so this side we call it forward reaction. So this is undergoing forward reaction. That is why the symbol is going this way. Now, under the reversible, we are seeing that after the product has been formed, it can also be broken down to reform or to help us get what we call it, our reactants back. And so that one is this side to this side is what we call the backwards reaction. And so anytime we see what we call a sign like this, then we are talking about a reversible reaction. That means the reactants, when they are formed into products, the products can also be broken down to form back the reactants. I hope I've made myself clear. And you use this reversible sign. So that is it. That means it's reversible. It can be forward and it can also be backwards. So that means this can form into what do you call it? This can go into what do you call it? Product, and can also be reversed back to reactants again. Now, for instance, let me give a typical example. In a salt formation, it's a reversible reaction. It's a reversible reaction. So we can decide to crystallize the salt and crystallize the water around the salt and give us the salt. And we may also decide that per other experiment, we can also try and get back the salt or the salt water back. That is basically it. So the salt water can be crystallized to give us the salt crystals or the salt particles, and it can also, however, be done in a different way to also give us the salt water back. And so that's a typical example of reversible reaction. Now, so we can define a reversible reaction as it is a reaction which can be made to go both forward and backward directions depending on the conditions on which the reactions is carried out. So a reversible reaction is a reaction which can be made to, so let me just try and define it. So a reversible reaction is a reaction which can be made to go both forward and backwards direction. So it can go both forward and backwards direction depending on the conditions carried on, regarding on the conditions on which it is carried, on which it is carried on, or on which the reaction is carried on which the reaction is carried on. So a reversible reaction is a reaction which can be made to go both forward and backwards direction, depending on the conditions on which the reaction is carried on. Now there is a symbol for a reversible reaction. So there's a forward and there's a backward. That's what it means. So there's a sign for the reversible reaction. Now a reversible reaction can either be a physical reaction or a chemical change. So it can either be a physical change or a chemical change. Basically, that is it. An example of a reversible physical change is heating of iodine and cooling of iodine. So when I have iodine, when I heat the iodine solid, the solid iodine is a typical example of what they call it. So iodine, you can also use salt like I did. So this is when you heat it, there's a forward reaction, heating. When you heat it, you can get your iodine gas. You can get your iodine gas. Now, when you decide to cool this gas, you can get back your iodine solid. So this one will be done by cooling. But however, it is a reversible reaction. So this can be broken down to come and get the solid by cooling. And this can be heated to get what they call it. This that is it. So this is a typical example of a reversible physical change. Reversible, if you did mixtures, you understand this in core. A reversible physical change. A reversible physical change. Example of a reversible physical change. That is it. Now, we can also talk about the reversible chemical change. A reversible chemical change. Let's write it here. Example of a reversible chemical change. Example of a reversible chemical change. Now, you can have hydrated copper. That is Cu. That's copper salt. I think so. Cu, a reversible copper, hydrated. So copper sulfate. That's a salt, copper sulfate. So when you heat it, you can come and get. The copper salt itself. Cu, copper sulfate, plus the water after heating it. So that means you have separated the water from it. Now, so this is white. The whole of this is blue. After heating it and taking away the water, it becomes white. Now, when you add water, you come and get this one back. So this one. So when you have this, a reverse, the forward reaction, that means if you have a hydrated copper salt or copper sulfate, hydrated, that means copper sulfate with water. We studied this when we were doing crystallization something, and the acid and salt. So this one has water. So before we can be able to take away the water surrounding the salt, we have to heat it before we can get it. So the water has now been separated. Now, if we want to get it back, then we would have to add the water to it. So it's reversible. I hope I've made myself clear.
Yes,
Now,
sir.
a chemical equilibrium is said to be established in a reversible reaction when the rate at which the reactants form product is equal to the rate at which the products break down to reform the reactants. And so a chemical reaction is said to be established, an established what you call a reversible reaction when the rate at which, that means the time it takes or the speed it takes the reactant to form the product, it's also the same speed you also take the product to break down to form the reactants. Then we are saying that the chemical what do you call it, equilibrium is established in a reversible reaction. And so the time it will take this to come and form this, it will also take that same time, that same rate to come and form this. It will take this same rate to break down to come and form this. I hope I've made myself clear. So equilibrium reaction is a reversible reaction in which the rate of forward reaction is equal to the rate of backward reaction. So in this case, the rate of forward reaction is equal to the rate of backward reaction. And so we can see that rate of forward reaction. And so if mathematically we are going to this, and then we can see that the rate of forward reaction, I can just do some mathematics here. The rate of forward reaction, So I can just say that means of the reactant. So I can see the rate of forward reaction of the reactant. So rate of reactant dt should be equal to the rate of what? Product. The rate of product should be equal to the rate of product. Basically, that's what it means because they are reversible. And so equilibrium reaction is a reversible reaction in which the rate of forward reaction is equal to the rate of backward reaction. So you can define it that way. When you're asked to define what do you call it, equilibrium reaction, you are saying that's a reversible reaction in which the rate of forward reaction is equal to the rate of backward reaction. And so to maintain a chemical equilibrium, the conditions establishing the equilibrium must be kept constant. That means the conditions that establish the equilibrium must be kept constant. Now, if the conditions are not kept constant, then that means we may not be able to get the rate of formation of the product to be equal to the rate of breaking down to get the reactants back. I hope you get what I'm trying to say. So the conditions under which this was able to form the product should be the same conditions under which this is able to break down to form back the reactant. So the conditions must be constant or fixed. Now, if there's a change in condition, then that means it will affect the reaction. That means it will no more be equal to the rate of formation of product, or the rate of forward reaction won't be equal to the rate of backwards reaction. I hope I've made myself clear.
Yes, sir.
Now, the reversible reaction in a closed system is said to be in a dynamic equilibrium. When you have a reversible reaction and it happens in a closed system, a closed system, like this bottle is a closed system. This is a closed system. That means there's a blockage between the system and its surrounding. And so heat is not given out, heat is conserved or something. And so a reversible reaction is in a closed system. It's said to be a dynamic equilibrium. It's said to be in a dynamic equilibrium. And so when a reversible reaction is in a closed system, it is said or it is assumed to be in a dynamic equilibrium. Now, when we say a dynamic equilibrium, we are saying that a dynamic equilibrium is reached when the composition of the reactant mixture. A dynamic equilibrium is reached when the composition, that means the makeup of the reactant mixture, remains constant and does not change with time. Are you getting it? So when I have, for instance, if I'm doing when I'm cooking or anything, there's a closed system. So the dynamic reaction is achieved when the composition in this bottle remains constant and does not change with time. It remains constant, does not change with time. That is, the forward and the backward reaction proceed at equal speed. That means the forward and the distance proceed at equal speed, and as a result, it balances each other and prevents any change in the composition of the reactant mixture. Because in a closed system, when the systems are kept constant, there won't be any change in the composition of the reactant mixture. When that happens, we are saying that a dynamic equilibrium has been achieved. Now, an equilibrium composition in a given reversible reaction normally depends on the composition of equilibrium, on an equilibrium composition in a given reversible reaction depends on, number one, it depends on temperature. So that means temperature can have an effect on it. It also depends on the pressure, especially on the gases or for the gases. It also depends on the concentration. And so equilibrium composition. So before something can be at the equilibrium, the composition is dependent on the temperature, the pressure, and the concentration. Ruben, ask your question.
So please, how does temperature affect equilibrium?
So, okay, so for instance, you said I was using this system. So for instance, if I'm using this system and we are saying that the rate of forward direction, or the rate of what do you call it, forward reaction must be equal to the rate of backward reaction. Now, if I decide, and it will be okay, it will okay when conditions are kept constant. So for instance, if I'm doing the experiment or I'm doing my reaction at maybe 60 degrees Celsius, then that means I should be able to maintain the 60 degrees Celsius over time so the reaction is over. Now, if I decide to increase the temperature to maybe 70, then that means I'm altering a change. And as a result, it will affect the reaction or it will affect the equilibrium. Do you get what I'm trying to say? And so you realize that, for instance, this
Yes.
water, the water in this, you realize that immediately I shake it small, you realize that it is shaking. Now, to a certain point in time, it will be normal or it will be stabilized. Then we are saying that the water in this bottle is at equilibrium. You realize that it is still shaking. That means if I shake it, I've caused a change in it. Are you getting it? Likewise, for instance, if this heat was applied to this, then definitely the heat will change the equilibrium of it, the equilibrium state of the water in the bottle. Do you get it? And the same way, when you reduce the temperature to it will also listen. So that means the temperature at which this was kept equilibrium must be constant with time. So we are saying that the equilibrium composition, the compositions in the reversible reaction depends on temperature, it depends on pressure, it depends on concentration. Now, when you introduce a catalyst into a chemical reaction, it normally has no effect on its composition. So the catalyst really has no effect on its composition. You know, catalyst normally doesn't take part in a chemical reaction. It only speeds up the chemical reaction. And so catalyst introduced in a chemical reaction or a chemical equilibrium has no effect on its composition. It has no effect on its composition. So basically that is that. And and the dynamic equilibrium can be reached from either directions. That means from both the forward direction and the backwards direction. That is it. Let me just give you a graph to illustrate the forward reaction and the backwards reaction. Then we continue. Then we continue. These are some points under equilibrium that you have to know. Can I please clean the board?
Yes, yes.
I'm coming, please. So good. So this is just a graph, a typical graph to illustrate equilibrium. To illustrate, so a graph of rate plotted against that of last time. You can draw this one. Here you can write amount of reactants. Let me just type it here. The AMT is amount of reactants. Amount of reactants and products remain constant. When it gets to this point, we are saying that equilibrium has been reached. That's why it is a straight line. Equilibrium has been reached. Please, it's not crooked, it's a straight line. Now, this part is a forward. This part shows a forward direction or the forward reaction. Forward. Then there's a forward reaction. I'm coming, Ruben. I'm coming. The Ruben, ask a question.
Please, what will show the difference between the forward and then the backward reaction in the diagram?
I'm coming. So in the diagram, there's it. The line coming this way is a forward reaction. It just shows the forward reaction. And this one coming this way shows the backward reaction. It's just a diagram to show this thing. Now, when they meet at this point, then we say that they are at equilibrium. So there's a straight line. So you are saying that when they meet at a point and the equilibrium has been reached. Sorry, this is reached. Has been reached. And the amount of the product, the amount of reactant and the product must remain constant before equilibrium must be reached. Are you getting it? So there's this one shows the backward reaction, and this one also shows the forward reaction. Now, when they get to this point and they move smoothly, then you are saying that equilibrium has been reached. And as a result, when equilibrium is reached, we know that the amount of reactants and the products remain constant because it's, let me see, in layman's reason, I see that calm has been restored. Let me put it that way. Now, energy change at a dynamic equilibrium is zero. Energy change as a dynamic equilibrium is zero. And normally at equilibrium, the energy change in a forward reaction is equal to energy change in a backward reaction. Energy change in a forward reaction is equal to energy change in a backward reaction at equilibrium. At equilibrium. At equilibrium. At equilibrium too, reactants and products have different quantities than were present initially. So when we get to the mathematics, I'll explain all these things. Now, if you are done, let's continue so that I'm done. Can I clean a board? Can I wipe the board?
Yes, sir.
One of these ends, you join again, and then we finish it up. We do some mathematics. So now let's talk about the dynamic equilibrium. Dynamic equilibrium. I've already explained what dynamic equilibrium is. Equilibrium. And we are saying that dynamic equilibrium can be categorized or can be grouped into two: homogeneous equilibrium, homogeneous equilibrium, and heterogeneous, heterogeneous equilibrium. Now, let me explain what homogeneous and heterogeneous means. Now, when we say homogeneous equilibrium or systems, let me put it that way. Homogeneous systems, let me just use that one, or equilibrium. Now, under the homogeneous equilibrium, homogeneous systems comes into play. Now, let me just explain what I mean by homogeneous systems. For instance, if you have reaction, you realize that anytime we write chemical reaction, sometimes we add the states of the reaction or the phases of the reaction or the products, or in other words, the molecules or the compounds. So for instance, if you have compound A, you realize that normally then you write something like solid, or you write something like gas. I hope you've seen this one, or aqueous. Now, under homogeneous equilibrium, what do you call it? They are all in the same phase. They are all in the same phase. That is to say that all the compounds reacting, all the reacting compounds are in the same phase. As a result, the product will be in the same phase. And so that means if they are all gas, then this will be also be in gas. Now, when we see something like this, then I'm saying that they are in, and definitely if the sign is like this, then we are saying that homogeneous equilibrium. Now, hetero means a mixture of both gas phase and a mixture of different phases. And so gas and solid, or gas and liquid, and so on and so forth. I hope I've made myself clear. So the homo is when they are in just a single phase or in the same phase. So for instance, if it's solid, then that means it's homogeneous equilibrium, and this is it. Or there's a homogeneous equilibrium reaction. If they are in different phases, then we are saying that heterogeneous equilibrium reactions. That is basically it. Have I made myself clear?
Yes.
Now let's do the equilibrium law and equilibrium constant. Equilibrium law and equilibrium constant. We are privileged to do what we call the rate of reaction. Under the rate of reaction, we spoke about the rate constant and so on and so forth. Basically, use a similar principle or a similar format, so it won't be very difficult to capture it. Now, when we say the equilibrium law, let me just write it so that you can let me. Now, the law of mass action states that the law of mass action states that the rate of chemical reaction is at a fixed point at a fixed temperature is directly proportional to the product of the concentrations of the reactants. So there is the equilibrium law states that the mass of the law of mass action states that the rate of chemical reaction at a fixed temperature is directly proportional. So here we are talking about fixed temperature. I told you when Ruben asked the question. So it should be at a fixed temperature. So the law of mass action states that the rate of chemical equilibrium reaction at a fixed temperature is directly proportional to the product of the concentration of the reaction. Directly proportional to the product of the concentrations of the reaction, or the concentrations of the reaction. And so, for instance, if I have for the reaction, when you have a reaction, if you have a reaction for a reaction A plus B, equilibrium reaction. So A plus B giving us C plus D. The rate of forward reaction will be that this is going forward and this is coming backwards. So the rate of forward reaction will be equal to, we've done rate, so that will be, this is a constant, so the constant of the forward reaction times the product of the reactants times the product of the concentration of the reactants. So what do you call it? The reactants are A and B. Now, if they have, what do you call it, just as we did in the rate, if they have coefficients, you raise them to that power. That is it. So the rate is equal to the rate of forward reaction. That is Kf. That's the constant of forward reaction, is equal to the product of the concentrations. When the 10 cuts, you what do you call it? You join again. So the rate of the forward reaction. So rate of forward reaction is equal to the constant of forward reaction by the product of the concentrations of reactants and the reactants. So A plus B, or A and B. And the reactants are doing the forward reaction, and this will do the backwards reaction. So we will also find for what they call it, the rate of backward reaction.